Hey everybody, in this lecture, we discuss evaluating classification models. Evaluating a classifier is arguably more complicated than evaluating a regression model because of the fact that in classification problems, we are working with categorical labels. And if you recall from the previous lecture, in these cases, we have probabilities that each data point belongs to one of these classes. Therefore, since we're working with probabilities and categorical labels, we cannot simply use the Euclidean distance to measure the difference between actual and predicted labels. And we have to think about more advanced techniques to evaluate classification models that take into consideration the fact that our classifier provides probabilistic measures. In practice, there are multiple ways to evaluate the performance of classification models. This can be as simple as a single number, which I call it here a score. It can be a matrix, or it can even be a curve. And in this case, I have summarized the main techniques that we can use, including decision boundary. And this first approach typically can be used when you have only two input features, meaning that you have a 2D problem or two-dimensional problem. And it cannot be used if you have 4 or 5 or more features. If you have 3 features, you might be able to use 3D plots, but still that's kind of challenging and difficult. Therefore, decision boundaries are mainly used for 2D problems where we have only two input features. But we have also other techniques that they can be applied to any number of input features, such as confusion metrics and other scores such as precision, recall, F1 score, precision recall curves, and receiver operating characteristic or ROC curve. So you can see here, we have a long list of different metrics that we can use. And we're going to start with decision boundary. Although this may not be applicable all times, it is something that allows you to have very nice visualizations of your classifier and how they perform. So it is very nice when you can work only with two input features. In order to understand how we can create and plot decision boundaries, let's have a warm-up example. And let's say we want to create a 2 grid of coordinate points using this numpy's method, which called meshgrid. And then we will show you how we can combine these together to create a list of x and y pairs. So what this means before going through details, so let's say I want to create a 2D grid where the x values are either 1, 2, or 3, and the y values can be 4 or 5. So this is a very simple problem because we have 3 different values for x, 2 different values for y, and therefore we have 6 different combinations, right? So you have 1 and 4, 1 and 5, 2 and 4, 2 and 5, 3 and 4, and 3 and 5. So this seems to be very simple, but we have to be able to implement this efficiently using tools from Python. And there are multiple ways to solve this problem, but I'll show you one way where we can use this numpy's meshgrid method. So the very first thing that you do, you pass these two 1D arrays. So X is a 1D array, Y is a 1D array, and we pass this into np.meshgrid. And the easiest way to explain how this works is to run this cell and be able to look at these outputs of this np.meshgrid. So you can see that we have two outputs, the uppercase X and the uppercase Y. And the way that X is, we have 1, 2, 3, but it's been repeated 2 times. And why 2 times? Because Y has 2 elements, right? Because remember, here you want to combine these two 1D arrays. So the way that this works is that the number of times that you repeat one of these arrays is actually related to the number of elements that you have in the other array. So that's why here we have 1, 2, 3 as the first row, and the second row is repeated again. However, for y, for this second output, if you look at here, there is a subtle difference. And the difference is that we have these 4 and 5, but 4 and 5, they are not in one row, they're actually in the first column. It's a little bit hard to see here because this is not aligned, but you technically have 4, 4, and 4. So 4 and 5 now is in the first column. And how many times we have to repeat this column? That depends the number of elements that we have in the other array, which is this original X array. And since we have 3 elements there, this means that now we have 3 columns. And here is the next thing that you need to do. So we have these 2D arrays, X and Y, and we can flatten them to make them 1D arrays. And the way that this rabble works in NumPy is that you keep the first row, which is 1, 2, 3, and then instead of going to the second row, we put this 1, 2, 3 right after that. So you can see that now it's a 1D array or a flattened version of this 2D array that we have for X. And similarly for Y, right? So remember, everything it starts row wise. So you have 4, 4, 4, 3 4s, and then you have 3 5s. And here's the nice thing. If now I put these two 1D arrays next to each other in a vertical position, which means that we want to concatenate them column wise. So that's why this np.c, the C stands for is for column. Then I get 1 and 4, 2 and 4, 3 and 4, and 1 and 5, 2 and 5, and 3 and 5, which means that now we have the 6 combinations that we were looking for. So just to wrap up, you can see that here we explain these, the two main things that you have to use, np.meshgrid, and also the concatenation that you have to do column-wise. And the approach is relatively straightforward. You create two 1D arrays, you pass them to np.meshgrid, you flatten them, and then you concatenate them, and now you have all possible combinations of these X and Y values. And again, I would like to emphasize that this is not the only way to solve this problem, but this is one way that you can do to solve this problem efficiently. So now, given what we have done here to understand how we can create these 2D grid points, now we can focus on a real-world data set. And this is what is known as the iris flower data set. And in this case, we have 4 input features. So there are these 2 parts, sepal and petal, and we have length and width for each of them. So this means that in total, we have 4 features. And the outputs here are categorical, meaning that we have 3 species. These are the names for these 3 species. And the goal is that we want to predict the category of each flower based on these input features, right? About the shape and size of these flowers. So to get us started, since this is a very popular data set, this is already part of scikit-learn. So in scikit-learn, there's a module called datasets, and we're gonna import this load underscore iris. And then in order to access this data set, we just have to call load underscore iris, and we can say as frame equals true. So this gives us a data frame. And in order to understand how this works, we can run this cell, and you can see that if we create a list of this object that we have here, so we convert this to a list, we have these names or keywords, right? Data, target names, which is very clear. The data is where you have your input features. The target is where you have your outputs. You also can access your target names, meaning that those are species that we have, feature names, etc. And if you're wondering what this iris object is here, since we are working with Python, we can use type, and you can see that we get something called this bunch, which means that if you like search for this is very much similar to a Python dictionary, which means that you have key value pairs. So these are the keys that we have. And if you just say iris and provide the key, you can see what we have inside this key. And that's exactly our data frame that we were talking about. So you can see that we have 4 input features. These are the columns, sepal length, width, petal length, width. And then we have 150 data points and 4 features that are placed in columns. One thing that we can do is to look at the target column of this iris or the keyword, right? So these are all our input features here, but we can look at the target, which are the outputs, and use this method, which is called value counts. And this tells us how many different labels or outputs we have and their counts. So we have 50 data points from class 0, 50 data points from class 1, and 50 data points from class 2. And if you're wondering what these names are, so these are the 3 categories that we have corresponding to 0, 1, and 2. So now that we have done a very simple exploratory data analysis, we can start with our logistic regression model and evaluate and see how it works. Can it really separate these classes or not? So we're going to import logistic regression from Scale-Learn's linear model. And the reason that this is part of linear model is because the underlying assumption that we have in our logistic regression model, where we discussed before, is that we have a linear transformation of data. And the only nonlinearity that we have is the sigmoid or logistic function, but we use that only to convert that real valued number or the logit to a probability score, right? So that's like the only reason that we are using the sigmoid logistic function. But as you're going to see, actually, logistic regression is a linear classifier, which means that it finds a linear function that separates classes. Something we have to do here because of the fact that we want to plot a decision boundary, and we can typically do that in a 2-dimensional space, is that we are going to only work with 2 of the input features, petal length and petal width. So this means that we are already ignoring some of the input features, which can cause some performance degradation. But for now, we use only these 2 input features and see how this classifier performs. The other thing that we want to do, because most of these metrics that we talk about in this lecture are easier to use when you have a binary classification problem, is to convert these 3-class classification problem into a binary classification problem. And this is something that we can do by putting this condition that we want to check whether the target label is equal to 2 or not. So anytime we have a yes or no question, that's a binary classification. Then the next thing that you do in terms of implementing logistic regression, we have to initialize this, right? Because this is the class, so we need to create an object. We use the .fit method. We provide the x and y values. And here you can see the whole idea about using meshgrid and np. Concatenating column-wise. This is just to make sure that we can create a 2D grid where the x values are from 2.9 to 7 and y values are from 0.8 to 2.7. And the reason that we do this is because I've already looked at the maximum and minimum values for each of these input features, and I figure out that these 2 numbers are very reasonable. And then the third argument here is the number of equally spaced points we have in this interval. So given that the x interval is larger, I decided to choose more data points, but this shouldn't really change your result very much if you modify them. You can, for example, use 20 data points for your x, 20 data points for your y axis, but it's something that you can obviously adjust. And so what we do, we create this 2D grid, right? So I can just run this and show you. So if I look at x underscore new, and let's look at the first like 10 rows of these. So you can see that we have 2.9 and 0.8, 3.11, 3.33, right? So these are these 20 data points that we have from 2.9 to 7. And right now, all the y values are fixed. But again, we are only looking at the first 10 elements. If we look at the shape of this, we can see that we have 200 rows or 200 data points, each with 2 dimensions. And that makes sense, right? Because we have 20 values for x, 10 values for y. So that's 200. Okay, so I can just delete this cell. And so the other thing is that once you create these data points, these 2D data points, Now you can use this predict underscore proba method for logistic regression. And what this does is that this gives you the probability scores for each of those 2D coordinates that we have. So if I, for example, right now look at the first 5 rows of this Y proba here, you can see that we get 2 elements in each row. And the reason for this is because we have 2 classes. So the first here element means that the probability that the first data point belongs to class 0, the probability that the first data point belongs to class 1. And the same thing for the rest of them. So you can see in this case, it is very clear that all of these data points belong to class 0 because it's almost 0.99 probability. And then the probability that belong to class 1 is actually very close to 0. And this is, again, something that we want to emphasize here, because when you use classification models, especially in this context, logistic regression, these methods do not provide class labels by default. What they do provide is the probabilities that each data point belongs to one of those classes. And then we can interpret and say, well, what should be at least the probability or the minimum probability to assign a data point to one of those classes, right? So in this case, it is common in many cases we put it at 50% or 0.5, meaning that if the probability that one data point belongs to one class is more than 0.5, then we claim that that data point belongs to that class. But we can obviously adjust that threshold, and that will become very important later on when we talk about precision recall curve that we have. So I want to kind of like emphasize on the fact that in this case, we get probabilities. So the nice thing is that now that we have information about all these probabilities, what we can do is that, let's say here we want to find or plot the probability that each data point in your 2D grid belongs to class 1. So that's how we select that. We can also reshape that to make sure that we have the right shape. And then we can use the contour plot. So we have already seen contour plots, and this is nice because what it does, it connects data points that have the same level or the same values, right? So we provide the XY coordinates, and our Z coordinate here, the third one, is actually these probabilities. And now we can pass this to this C label from matplotlib to get nice contour plots with the labels that we have here. So here is the final product, right? So you have 2 features, petal length and petal width. And this coloring that you can see here with these numbers, it shows us all the data points that are on this line. They belong to class 1, which is the green class, with probability 0.9. So everything that is on this side, on the right side, belongs to the class green or class 1 with probability equal or greater than 0.9. And everything that is on the left side, the probability is less than 0.9. But how fast that probability changes, so you can see that now we have these contour plots that shows us that this probability gradually decreases. And of course, if, for example, we are on this purple line here, the probability that this belongs to the green class, it's very close to 0, right? And that's why you can see that you get 0.50. And that's one nice thing about like binary classification problems, because if we know the probability that all the data points here belong to class green, then the probability that they belong to class, let's say blue, is 0.85, right? Because it's 1 minus this number. So it makes the plot much easier. So as I said earlier, usually when we talk about the decision boundary, by default, we mean that we want to find data points, or in this case, like curves, that it gives us the probability that is 0.5, meaning that all the data points on that line or curve, it's 50% likely to belong to one class, and of course, it's 50% likely to belong to the other class. So that's the most uncertain part. And then if we move to one direction a little bit, then we get a little bit more confident that that data point belongs to that class. So how can we find that? Meaning that how we can find all these XY coordinates here such that the probability that we get from our classifier is exactly 0.5. It turns out we can actually solve this problem analytically. And if you remember from before when we had the sigmoidal logistic function, if you look at where we get probability 0.5, we had this example that we showed that if the input to the logistic function is 0, then the output of logistic function is 0.5. So this means that that linear combination of input features, which is W0 plus W1x1 plus W2x2, if that equals 0, and then we pass this 0 to the logistic function, we get 0.5. And now if you want to find the connection or relationship between x1 and x2, once we solve the problem, meaning that now that we know the optimal values of these weights W0, W1, W2, this is relatively straightforward because we can assume one of these two, for example, like x1, is the independent variable, and then find x2 as a function of x1, right? So if we do simple math, where we just, for example, can take everything, this W0 plus W1 x1 to the other side of equality sign. So that's where we get this negative sign, and then divide everything by this constant here. We get this nice relationship between x2 and x1. And in order to plot this, we just have to give these values of independent variable x1, which again here, since we want to draw a line, we only need 2 points. I assume that this takes two values, 2.9 and 7. And in order to have access to this W0, W1, W2, we can look at the coefficients of this logistic regression model, which is now trained. And so there are values in these coefficients. And for finding the first coefficient, we need to use index 0. And for finding the other coefficient, the second one, we use index 1. So in some sense, this is W1 here. And this term that we have here is W2. So before we started indexing from 1, now we start from 0. And also we have this W0, and this is what is known as the intercept, right? So the way this is in secular, we always separate intercept from other coefficients that we have here. So this means that now if I run this cell, I can find 2 points on that line that gives us this 0.5 probability. And so compared to before, the only thing I'm adding is this line, which is length and width as x and y values, or x1 and x2. That's what I call here, because I don't want to use the term y, because y usually for us refers to the targets or labels. So that's why, sometimes we use only x for the input features. But, it's exactly the same idea, just different ways of naming variables. So if we now plot this, so this new line is plotted as a black line and is dashed too. So you can see that this line is the 50% line. So if we decide, so this is something that we can, it's in our control what the threshold should be. But if we decide that we want to be very fair and we put the decision boundary at 50%, then this black dashed line is our decision boundary. Anything on the right side belongs to class 1. Everything on the left side belongs to class 0. And if you really want to know how these probabilities change as we get farther from this line on both sides, obviously you can plot these contour plots, and that gives us a lot of information. But what I'd like to emphasize again here is that if we want, we can put our decision boundary at 0.9, meaning that we only label a data point as the green class or class 1 if we are at this line or on the right side. And then everything on the left side, even including what we have here, will be labeled as 0 or blue here. So we have the option to choose the decision boundary and the corresponding or the associated probability. So that's the first approach, decision boundaries. And it only works, obviously, when you have 2D data points. If you have 1D, still you can apply it, but doesn't look very nice. If you have 3D, it becomes a little bit more complicated. And more than that, we cannot really visualize something in a 4 or higher dimensional space. So now let's go talk about the second metric that we discussed, and that's confusion metrics, which is very helpful for binary classification problems. In this case, we are using our machine learning data set, which is called the MNIST dataset. And MNIST is one of the, again, most popular benchmark data sets in machine learning. And the nice thing about the fact that this is included in scikit-learn is that we don't have to do any pre-processing. So this data set is ready to be applied to different machine learning methods. Unlike some of the homework problems that you notice that you have to do a lot of pre-processing, so this saves a lot of time for lectures. This data set contains 70,000 images, and each image is labeled with the digit it represents. And in this case, each image is relatively small or raw resolution. It's 28 by 28 pixels, so it's basically a 2D array. But since right now we don't know how to deal with 2D arrays as inputs, because most of cases right now we have only a one-dimensional input feature vector, and then we concatenate them for all of the samples to make them 2D, but one axis corresponds to the feature, one axis corresponds to the number of samples. But in this case, even for one sample, which is one image, we have a 2D array, right? So if we want to concatenate now all these images, we actually end up with a 3D array. And that's something that we have not covered so far. Therefore, what we do right now is that we're going to flatten each 2D array to make it 1D. And because we have 28 by 28 elements, so this gives us 28 square, which is 784 elements. So we can represent each image as a one-dimensional vector with 784 elements. And now if we concatenate all of these together, let's say all 70,000 images, we get a 2D array of size 70,000 by 784. And if you're wondering what these features are here, in this case, we have grayscale images, and these show the intensity values that are between 0 to 255 for different shades of gray, and 0 to 255. So we have all these shades of gray, and that's how grayscale images work. Also, to make sure that make this clear that this discussion in this lecture applies to any classifier, not necessarily just logistic regression, we are going to use what is known as the SGD classifier. And one thing I want to show you here is that what we have covered so far gives you really good information of a lot of these built-in machine learning methods in scikit-learn. So if you look at here, you can see that this SGD classifier obviously uses a stochastic gradient descent, which we are familiar with, and we covered this. So it means that we have a loss function, we find the gradient of loss function, and then we can start from a random solution and makes it better iteratively, right? But the only difference here is that this loss function that we can use can have actually, different forms. So the only one that we really covered so far in this course is this log loss, right? Because remember, with the cross entropy loss, we always have log of probability. So that's why this is called log loss. But as you can see, this can be applied to various types of loss functions, which is really nice, right? This is the really nice thing about gradient descent methods, because they are not only restricted to a like only one class loss function, and it can be applied to multiple ones, as long as we can find the gradient of loss function, and then the rest is very straightforward. So we're not going to go focus too much on this, but you can see that this is a classifier. We can choose the loss function, then we can automatically find the gradients, and start from a random solution, make it better. And also you can see we have a lot of parameters we have seen with stochastic gradient descent, such as learning rate, and so on and so forth. So in this case, we are gonna import the MNIST dataset. This will probably take a little bit longer than the first data set we had with iris flower, because we have significantly more data points. But as you can see, this is very similar to this with the object that we had for the iris flower. We have this data, target, categories, feature names, etc. And if you look at the data part, you can see that we have 70,000 data points, and each data point has 784 elements. And this is because of the discussion that we have 28 by 28 pixel images, but we can make them flatten. And also we have 70,000 labels. Something I want to make sure that you also pay attention to here, that these labels, they have these quotation marks around them, which means that these things are not actually integers and they are strings, right? That's how we show strings in Python, like for example, what we have here. So based on our conventional notation, we have the data metrics, which is X, we have the targets, which are Y. Again, let's look at the labels that we have, and you can see that these labels are actually strings, right? So if you're not sure about that, you can always use type, and this confirms that. Also, in this case, because we want to evaluate the classifier on the testing data set, we have to do train test split. Since the data has been already shuffled or permuted, we can just, let's say, use the first 60,000 data points for training, and then the remainder for testing, right? So this means that up to index 60,000, and this means that from 60,000 to the end of the list. The next step that we have here is that we want to also convert this to a binary classification problem. So similar to before, we can put this condition that whether the label that we have either for training or testing data is equal to 5 or not. So this means that we want to only detect digit 5, and the answer is yes or no. And therefore, because of this, we have a binary classification. And you can see that in this case, we get a bunch of these trues and falses. Again, true means yes, false means like no. And we can provide this directly to the classification models that we have. Okay, so now that we have these labels, now we can select a classifier and train this classifier. So we're gonna import SGD classifier. We're gonna also use this cross-val score. And in order to understand how this works, we can go to the documentation page of scikit-learn. And this is a very nice way of measuring accuracies. And the way that it works, let's say if you use like a cross-validation with 5 folds, we divide the data into 5 folds, and then at each time we use 1 fold for testing, that's the blue color, and then we use the remaining folders, meaning that these 4 folds here, for training. And then we change the fold that we use for testing. So this way we can test the entire set, but not at the same time, right? At different levels, and we can measure accuracies. And something also I want to mention here about this scoring equals accuracy. So this is the simplest way of measuring accuracy, which is the fraction of correct predictions over the total number of samples, right? So if you have, let's say here, 60,000 training data points, 10,000 testing data points, and out of the 10,000 testing data points, you make correct predictions in 9,000 cases, then you get 90% accuracy. And the nice thing is that in this case with cross-value score that we just imported from scikit-learn's model selection module, we provide our classifier, we provide our entire training and testing data set, and the only thing is to provide the number of folds that we want. And here I choose 3, and this function or this method will automatically divide the data in the format that you saw, and then report the final accuracy scores for us. So this is gonna take a little bit of time because we have to do 3 times training and 3 times testing for each fold. But we should be able to get the results relatively fast. And you can see that in this case, we get these 3 accuracy scores, right? So this means that on average, our classifier is about 95 to 96% accurate. And we may get really excited about these accuracy scores because these are really high scores, very close to 1 or 100%. But let's do something to make sure that we are not actually missing something. So from scikit-learn, we're going to import this base estimator. So this means that what we want to do is that define our own estimator. And since now we have this class that we inherit from this base estimator, this means that we don't have to necessarily like define everything from scratch. We can just inherit from this base estimator. And during the training or fit method, we don't want to do anything. And during the returning, during the prediction stage, what we do here is we just provide all zeros. And we also make sure that the data type is Boolean, so it means that we create false for every single testing data point, right? We return false in this case, which means that every time we get an image and we ask our never5 classifier what class it belongs to, the answer is that it's not digit 5, right? Because we have a binary classifier here. And so this is something very trivial and possibly it shouldn't work very well. But let's see what result we get if we run this. So you could see that like here, we got our results much faster. And this is because of the fact that we are not doing any training, right? So for training, we're just passing. And we just provide false every time we get a testing data point. So what this means is that even if we don't do anything, here we get 90% accuracy. And here you can see one of the biggest problems with just the standard accuracy score. And the fact that if we have an imbalanced data set like here, so recall that we separated digit 5 from the rest of digits. And what this means is that we have 10%, roughly speaking, digit 5, and 90% of our data belongs to the other classes. So the simplest thing that we can do, we can always say that, well, for a testing image, that doesn't belong to class 5. And in that case, because we have a lot more data points from the class that does not belong digit 5, then we get, about 90% accuracy, right? Because we have 10% of data points belong to class 5 and 90% to the other class. And so if we always provide false, on average, we get about 90% accuracy. So this means that the 95% that we got earlier, that's not really a good accuracy score, and it misses a lot of important information about this classifier, in a sense that we are probably not doing so great as these numbers here suggest, and that's something very important when you want to have a fair evaluation of your classifier. And in order to dig a little bit deeper into these, you can use again, like let's say we use our SGD classifier, we provide our training data, and now we predict the labels for these testing data points. And that's why I call here this y underscore pred. And one thing we can do from scikit-learn.metrics, so most of these metrics that we are going to cover today, they are in this module called metrics. We import something called confusion metrics display. So this line is just to make sure that we have the right figure size and font size, etc. But what this does is that we provide this method, which is called from predictions. So we say confusion metrics display dot from predictions, and we provide the true labels for our testing data sets, the predicted labels. And remember, these predicted labels right now are based on the 50% threshold, meaning that since we are using predict, these classifiers should give us a label, right? It should convert those probabilities into labels. And the way that it does that is based on 50%. So if something is more than 50% chance belongs to one class, then that's the label for that data point. So we provide the testing data point, the labels for testing data points, the labels that we predict for them, And then here also you can say that what these labels are, right? And because it's a binary classification, we can think of these as negative and positive. So we use -1 and 1 or 0 and 1. So that's something that we can decide. But when we are working with confusion metrics, usually it's more common to use the terminology negative and positive. So this may take a little bit of time here, again, because we're working with a larger data set compared to what we had before. On this confusion matrix, as you can see, it's a matrix. It has 2 rows and 2 columns. These rows correspond to true labels, which is negative and positive, or 0 and 1, or no and yes, right? So there are different ways we can think about this. And then we have the predicted labels. And based on this terminology, right? So obviously here we have the number of data points that fall into each bin or each part of this matrix. But one way to think about this is that if something belongs to the class -1 and is predicted to be in class -1, then that's called true negative. And the same thing with true positive, right? So if something really belongs to the positive class and predicted to be in the positive class, that's true positive. But we have, and these two diagonal terms are correct predictions. But now we have two types of incorrect predictions. And these are the terms that we have in off-diagonal terms. And the first one, this belongs to the negative class, but predicted to be positive. Therefore, it's a false positive. And the same thing with here. These data points that we have here, they belong to the positive class, but they predicted to be in the negative class, and that's a false negative. And you can see that in this case that we had before, obviously we have different numbers of false positives and false negatives. And you can see that most of our correct predictions are coming from the negative class, the class that does not contain 5. And that's consistent with our observation that we had before. So the next thing that we're going to discuss in the second part of this lecture is that what type of scores or metrics we can actually extract from this confusion metrics.